Alright, so today we're starting our next topic, which is, as it says there, trigonometric functions. We'll do some other trig stuff later where we're using trigonometry for doing measuring things. But for the moment, in this particular topic, we are looking at functions, trig functions. All right, and so because you might not have in methods just yet done so much on the trig functions, sine and cos in particular, a little bit more background here. So unit circle, as it says there, is a circle of radius 1 unit, and it's used to define the trigonometric functions sine, cos and tan. So this is where these particular things all come from. So if here's our unit circle. All right, so here we are, a Cartesian plane here. X and Y axis, we've got a circle there, centers at the origin, and these are all labeled 1, -1, -1, 1 here, because that's the radius is 1. So if we pick a point P here on the circle, so it's got coordinates X and Y, and we draw ourselves a triangle, right angle triangle, like I've got here, that dotted in that red there. Then the X value would be that length, the Y value would be this length here. All right, so by definition, so this is definition, the X coordinate of P is what we call cosine. So the X coordinate, which relates to this length here, is called cosine of theta. And the Y coordinate of P, and that's this length here, is sine of theta. So in other words, down here, X is cos theta and Y is sine theta. So from what we've been doing before in previous years, is our angle there, the opposite is the sine, and the adjacent is the X. So the opposite sine adjacent is cos, which we would have been used to using in the past when we're doing SOHCAHTOA. All right, so those numbers that you stick into your calculator, it uses an algorithm that those numbers that you get out from your calculator relate to the lengths of these sides. And of course the hypotenuse of this triangle is 1 because it's a circle of radius 1, i.e. the unit circle. All right, so that's sine and cos. Now for tan, we draw a tangent to the circle. Now tangent is a line that touches, and the one that we could have lots and lots of tangents, but the one we are interested in is the one that touches here. So this blue line, light blue line I've got here, that's the tangent to that circle. So by definition, if we got our point P, and if we extend that up to reach that tangent, then the length of from the x-axis up to here is what's called the tan. All right, so it's the tangent. Now if I put back in my other triangle, my sine and my cos, you'll notice now I've got two triangles there, a little one here and a big one there, which of course are similar triangles, and you can then, from using those similar triangles, come to the conclusion that the tan of theta is the sine theta over cos theta also. Okay, so by definition, it's the length, this length here, from the x-axis up to the point where this point C, where the extended radius hits the tangent. All right, so there's a bit of background about where those things come from, and you'll do more on that in methods. All right, so with this, there's what we would call some symmetry properties, all right, because we're going around in a circle. There's certain things in each of these four sections of the circle that are related to each other. And so we divide them into what we call quadrants. And so we start here in this section there, positive x, positive y. And we call that the first quadrant. And then we go around in an anti-clockwise direction. And so over here is the second quadrant, the third quadrant down here, and the fourth quadrant. All right, so there's relationship between angles in the, or sine, not angles, oh well, angles, yes there is, but in particular the sine and cos and tan values of angles in the second, third and fourth quadrant relate back to angles in this first quadrant. And so that's what we're talking about when we talk about symmetry properties. All right, so as we say here, excuse me, the values for sine, cos and tan for angles in the second, third and quadrants relate to values for the first quadrant angles. This we call the symmetry properties. All right, so here we've got some triangles. And so this point here, that's P1. And then if I go straight across here to P2, and then I'll draw some triangles. Now, this is a unit circle, so that length there and that length there is 1. And then I'll draw triangles there like that. Now, because this is the same length, that's the same length, this is the same length, that's the same length, then so is this, and this angle here and this angle here. Those two angles are the same. Now, if I follow this down into there, and I follow this one down into there, and then you'd follow that across, then this triangle down here for point 3 and this one from point 4, all of those four triangles are the same, and all of these angles down in here are all the same. So I call these angles down in here the reference angle, because that's the angle we reference back to the first quadrant. All right, now there's some things to look at when you look here. So sine is the opposite, so sine is this length here. And for the first and the second quadrant, you see that's above the x-axis, so it's in the positive y direction, so it'll be a positive value. Down here and here in the third and fourth quadrants, that length is in the negative, so it would be a negative value. For cos, we've got a similar thing. For these two quadrants here, they share that. That's positive for cos. But in these two quadrants, the second and third, this length here is on the negative x, so that that's negative for cos. All right, so all of those triangles, they're all the same, they're all congruent, and I'll just sort of talk through a few things. So here's a bit of a summary. Since all the triangles in the diagram above are congruent or the same, the sine, cos, tan values in the second, third and fourth quadrants have the same size as that in the first. And we refer to theta here, as I already said, called that the reference angle. And it's the angle between the radius and the x-axis, all right? So always remember, it's always back to the x-axis, this angle that we're drawing, right? So we're always doing this angle in here. Never this one up here or this one up here. Always this one down in here between the x-axis and the radius. All right, so I already talked through a bit about the values, the signs being positive or negative of sine, cos and tan. We can summarize like this. So in the first quadrant, they're all positive. In the second quadrant, sine is positive, but cos and tan are negative. In the third quadrant, tan's the one that's positive, the other two are negative. And in the fourth quadrant, cos is positive and the other two are negative. So you see up here in the red, this is something we can use. So starting in the first quadrant, going in the anti-clockwise direction, all right, which is the way the quadrants go. It's also the way we measure our angles from the positive x-axis in the anti-clockwise direction. But more on that later. So all positive in the first quadrant. So I'm just focusing on the positives. Sine is positive in the second quadrant. Tan is positive in the third quadrant. And cos is positive in the fourth. So if we underline each of those first letters, then we've got a little mnemonic that we can use, ASTC, or all schools teach calculus. All schools teach children, or many others that you can think of. All students talk crud, and whatever you use. All right, so what's the point of all of that? Well, we will get to what the point of all of that is. Well, I'll just give you a little synopsis. So that means if we know things about sine, cos, and tan in this first quadrant, then we can find the sine, cos, tan values of the other three quadrants fairly easily. And I'll show you a technique later about how we do that, and a technique that we can use for lots and lots of things. All right, so for some particular angles, there are what we call exact values. So exact values are precisely what it says, you know exactly what the value is. So might it be, so root 3 on 2, for example, 1/2, they're exact values, not decimal approximations. And so there we go, I said that. So exact values we need to know derived from the angles 0, pi 6, pi 4, pi 3, and pi 2. And in degrees, of course, that's 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees is what the degrees equivalent. These ones here are radian. All right, and so these are ones you expected to know in Spec and in methods, and then by knowing those you can then figure out a whole bunch of others. Now, how do we remember them? So a couple of triangles to help with pi 6, pi 4, and pi 3. So this triangle on the left helps you with the pi 6 and the pi 3. So say if I wanted to know the cos of pi on 3, I'll go to my pi on 3, and I know cos is adjacent over hypotenuse, so that's 1 over 2. All right, and if I wanted to know the sine of pi on 6, sine I know is opposite over hypotenuse, so it's also 1/2. All right, and then there's this relationship between these is something we'll look at. It's called complementary relationship. But more on that later. All right, so for pi on 4, again, you can just use this triangle here. All right, so for me, that's what I learnt when I was at high school, and I've used those two triangles ever since to remember those particular things. All right. Now for things like 0 and pi on 2, what I need to do for those is revert to the unit circle and remember the coordinates. The coordinates there are 1 and 0. coordinates here are 0 and 1. Coordinates here are -1 and 0. And the coordinates here are 0 and -1. All right, and so remember, x is cos and y is sine. And so if we want to know the sine of 0 is 0 degrees is across to this point, and the sine of it's the y value, so it's 0. And so on for all of those that are 0, pi and 2, pi, 3 pi and 2, etc. All right, so there should be a couple of handouts here, exact values, the lists, all 4 quadrants, symmetry, complementary properties. Then there's a whole bunch of stuff in there. Me personally, I don't use them. I would always draw a diagram and figure those things out, because there's a lot to remember, which you will see. And the exact values, I said, all 4 quadrants. Again, I don't remember all 4 quadrants. I use these things and these things to decide what the values will be. All right. So let us have a look how we actually use this stuff. All right, so here we've got a couple of examples. Yep. Evaluate each of the following. All right, so I'm going to put a big line down the middle there. Start here, there it is, big line down the middle. All right, so let me now, sine of 5 pi on 6. So what I do is I go, okay, let's draw myself. I always draw get rid of that, that's in the way. Let's put it, all right, so I always draw a rough sketch. Here's my unit circle. Remember, it's pi out to here, pi on 2 to here. 5 pi on 6. So 5 pi on 6 is short of pi. And this angle down in here, how much short of pi is it? Well, 6/6 is 1, so 5/6, so that's pi on 6 there, in there. Now that, as I mentioned before, that between the x-axis and there, that's my reference angle. All right, then what I do is I go, okay, all students talk crud. And I'll go, okay, so I'm in the second quadrant here, and sine, second quad, what that means is it's positive, because it's sine. Remember, these all ASTC, what's positive in those quadrants? So all students, so sine is positive in that second quadrant. Now, reference angle, already mentioned about the reference angle. And already figured that out to be pi on 6. So what we know then is that the sine of 5 pi on 6 is a positive value, and it's related to the sine of the reference angle. So it's related to the sine of pi on 6. And so then I go back to my triangles up here, and we're going pi on 6, the sine of pi on 6, opposite over hypotenuse, so 1 over 2, and so that's then equal to a half. All right, and so I'll do that for all the things. So I'll follow the same process here with this one. All right, there we are. -8 pi on 3. So 3 goes into 8 twice, so that'll be 2 pi's, and then we've got 2 left over, so 2/3 of a pi. All right, and the minus. So the minus means, so I should have put that in here, around to there, is 5 pi on 6. The minus means instead of going anti-clockwise, we'll go clockwise. Now we're going clockwise 1, 2 pi's, and then 2/3 of a pi out to here. All right, so that's negative 8 pi on 3. All right. So what do we got? Down here we're in the 3rd quadrant. And cos is negative. All right. Doesn't like that. I don't want to change all of that. But anyway, all right. Let's oh, I know what I can do. Go here, pretend to rub something out. Go here. There we go. So A, S, T, C. So in the 3rd quadrant, it's tan that's positive, so cos is negative. All right. Then reference angle. All right, reference angle, always between the line and the x-axis. So the reference angle is this one here. Now remember that was negative 2 pi and then another 2/3. So if that's 2/3 around to here, then it's got to be 1/3 to there. Because remember there's a whole pi in that. So that there is pi on 3. Oops, the 3 hasn't come out very well. There we go. So a reference angle equals pi on 3. So from that, the cos of negative 8 pi on 3 is a negative number, and it's related to the cos of pi on 3. So then we go back to our triangle. Pi on 3 cos adjacent over hypotenuse, and so that's a half again. So there we go. We've got equal to negative 1/2. All right. So that process is a process that I would use all of the time. Rough sketch, figure out where your angle is, figure out what your reference angle is, figure out whether it's positive or negative in that quadrant, and then refer to your triangles. Now, sometimes we're given information like this. So this is not one of the exact values, but we're given this particular thing. So sine of alpha is 0.4. Find the cos of pi on 2 minus alpha. Right, so I'll go again. I'll go, righto. Here's my unit circle. Here's my line there. It's safe to assume always that these angles would be in the 1st quadrant, and the sine of it, so if that's 1, the sine of it is 0.4. That length there, that's what we're talking about. All right, so pi on 2 minus alpha. All right, pi on 2 is to here, and then minus alpha. So we go pi on 2, and then minus alpha. Back this way. So that's alpha. So this angle in here, pi on 2 minus alpha. Now if I drop that down there, and we're after the cos, so we're after this length here. That's 1 again. Now this side of the triangle and the y-axis, been lazy and not labelled it, are parallel. So if this angle here is alpha, and this then alternating angles, this angle there is alpha. So now there's some similarities here between this triangle and this triangle. Now over on this triangle, because that's 1 there and that's alpha, the side opposite to the alpha was 0.4. Over here, this is 1 and this is alpha. So the side opposite the alpha, this one, through geometry, should be 0.4. So what can we go from that? Well, that the cos of pi on 2 minus alpha, this side here, is in actual fact 0.4 through that geometry, but of course that was sine of alpha. All right, so that's one of the not the symmetry properties, but the complementary properties. There, just looked at my notes. That's one of the complementary properties that I've used there. So, you know, I said earlier that I actually don't remember those things myself. This is the technique that I use. I look at those triangles. All right, so even though they don't look like they're the same, because I'm so talented an artist, they are in fact the same, those triangles. All right, so there's a fair bit in that, so you need to get a bit of practice on that. The techniques that I've outlined and shown there are quite new for you, so you need to take your time, and if you need help, make sure you ask for some, and as always, have fun.